Okay, so we start with basic concepts of fire protection, right? And I'll just have some little bit of introduction about the fire, little bit of introduction, then combustion process a little bit, then planning for fire protection, and then we'll define what is called fire resistance. Because if you are designing a building, quite often you will come across what is the fire resistance of an element. So we'll talk about that, and then we'll start with the effects of material. Now, if I look at design for fire resistance, okay, the sequence goes on, then detection, alarm system, suppression, smoke venting, escape and refuge. All this we will be talking about, some little bit of risk assessment. Now, if you look at fire strategy for any kind of nuisance, any nuisance you want to protect against any kind of nuisance, whether it is building or general environment or whatever it is. First thing is that stop at the source itself. Stop at the source itself. Don't allow the source to grow. That means avoid initiation of fire itself. So avoid initiation. Now, if you can't, accidentally initiation occurs, even after taking precautions, which can happen, then see that it doesn't spread. Its intensity, it doesn't spread over large space, its volume doesn't increase. That's true for anything, including even, let's say, we are talking of pollution today a lot, just digressing a little bit from here. So if you want to reduce down the pollution level in the city, actually I should see what are the sources and cut down there itself. And okay, you may be able to do it because there may be some constraints, so you may be able to do some, but you can't completely stop it at the source. Then see that how does it should not spread. Same thing goes for fire. We see that initiation should be stopped, avoid as much as possible, and if it is initiated, don't allow the spread to occur. Then if spreaded accidentally, because in case of fire it can happen that it is accidentally spreaded, then you should suppress it. And then in the meantime, you must ensure that people there should go to a safe refuge, escape out of the building, escape out of the. So this is the kind of strategy followed in case of fire. And recently you have seen that there are several cases of death, fire related death all over the world. The one in UK, recently one in New York, 12 people died. 12 people died. This was, you can understand, I can understand that in a country like India, this can, we are not so technologically well developed, and neither we are so much, our protection system is, like the system is so much well developed, but even happening in developed world. So anyway, this is important. So that's why fire is. So basically, if you see this, I am not very sure it is readable properly or not, but still what I will try to do is, I will write it on top of it. For example, this is control of combustion process, combustion process, control of combustion process. So that would avoid injury. So therefore, this depends upon what we will go into details, but just as an outline, quantity of the combustible material within the space, right. Then air supply, because as you shall see just next slide, that three things are essentially required for fire. One is the fuel, other is air, and it got to initiate, therefore you need heat. After that it sustains on its own. So you have to see this. So air supply comes from ventilation into the building, and combustible material present, that provides the fuel. And then it also depends upon the space, the volume of the room, etc., etc. We shall see that. Then since the heat has to dissipate through the envelope or periphery of the room, their properties are important, particularly thermal properties are important. So that's related to initiation. So you control, if you want to control them, you'll have to look into this. Then also you can do control by construction. That is what I was saying, structural fire design, protect structural elements. For example, you could not stop, I mean it has initiated on its own, accidentally, it should not be spreaded to the next room. Therefore, wall etc. should be designed in such a manner that fire does not go to the next space. Also, one of the major important thing would be the structural system should not collapse. So, that structural control, control by construction, control by construction. So, this is construction part of it, construction, control by construction, and then when it comes to suppression, automatic suppression. So, you can see it is written automatic suppression here. So, you can have sprinkler system, alarm system, etc., which we will discuss. And then manual suppression also could be there. You will see that manual firefighting systems are there, we will talk about them. So, that is basically the kind of strategy generally we adopt. See that initiation do not occur. If it occurs, then it should not get spreaded, and if it is spreaded, then it should be suppressed. And in the meantime, of course, you should take out the people should go to safe escape and refuse. That is the basic principle. All right. So, these are the three things required for fire: the fuel, most important, heat, and air or oxygen. I mean, air has got oxygen 21% or so. Therefore, that's three things are essential. Now, we will also talk about it later on sometime when we talk in suppression. I cut any one of them, then fire will stop, or I cut any one of them, fire will stop. And this will only, when it is finished, then again fire will stop. So, even fire suppression system or otherwise, the strategy comes from this. So, basic understanding is I need three things for continuation of the fire. So, how does it occur? Something like this. Let us say this is my fuel. Now fuel is what? Furnitures, wooden furnitures, combustible material. Many of them are combustible material, papers. Many of them are combustible materials. So, these are the, so this is why it is shown like this. These are the ones. Now, supposing for some reason or other this gets heated up. What will happen? Some of these molecules, this combustible materials, basically what happens is the molecules get broken down into finer molecules. The process is called pyrolysis. Basically, say wood or something, when you heat it up, or they are basically or polymers, they are large molecular weight material. When you heat them up, they become smaller molecular weight and might go as volatile. So, form volatiles, and for that it needs energy. So, when you have supplied sufficient energy, a time would come, then this will all get broken down into smaller molecules and can volatile mix with the air in the gaseous form, and combustion process, reaction with the oxygen will start. That is combustion process. So, you need heated up to what is called ignition temperature. Heated up to, pyrolysis will occur, heated up to ignition temperature. Ignition temperature. So, the ignition temperature generally would range from around 400 degrees centigrade, etc., maybe some of them even much less. But if you have inflammable fluid liquid, they instantaneously catch fire. So, that is basically the process of quick understanding of process of combustion. Now, once it has started, volatile started reacting, this itself generates heat. Once the volatile starts reacting with the oxygen, this process is exothermic. only then only the fire would occur. Fire is a gaseous, flame is a gas phase phenomena. Because when the combustion occurs, the reaction with the oxygen occurs, that is the combustion reaction, it would generate a lot of energy, dissipates a lot of energy, that is exothermic reaction. Some of the energy is in form of light, therefore you see the flame, right, otherwise it generates a lot of heat. So, this heat energy, again what it does? It supplies heat back to the fuel itself, supplies the heat generated will supply some heat back to the fuel itself, and then more combustible material will get pyrolyzed, and if sufficient oxygen is available, air is available, the combustion process will sustain itself till all the fuel is consumed, right. So, this is what it is. So, essentially this is the process of combustion, that is what occurs, and then we do a little bit of quantification also. We can talk in terms of burning rate m dot. I will define this a little bit later. M dot. Dot is usually, that is the nomenclature used in many books. So, dot is for rate, m is the mass. So, rate of volatile generation is what is defined as a burning rate. Rate of volatile generation, mass of volatile per unit area, mass of volatile, I will have a formal expression I think somewhere later, mass of volatile generated per unit area of the fuel, right, per unit time, that is what is we call as burning rate, right. And QF is the amount of heat generated, rate of heat generated, right. Part of this heat will go, part of it will it will heat up this, and then further heat will be generated, and so on and so forth. So, some heat would be required to evaporate them. So, one can actually get an expression, some will be dissipated outside, some it will be dissipated outside, we will look into that a little bit later on, right. Now, within a building what happens? Within an enclosure, you see, as the fuel goes on burning, or combustible material like furnitures, paper, etc. goes on burning, since it is a closed space, heat will not dissipate out completely. So, what happens is with time you find there is some amount of increase in the temperature, but fire starts at some corner of the space, the room volume, somewhere in the corner it starts, and once it starts, then temperature, average temperature of the room starts increasing slowly. So, initially slow increase would be seen, average temperature of the room. Localized in corner where the fire has actually occurred, it would go, the temperature will go high, but if you look at the whole room, it has not captured whole the room. But subsequently what will happen is, normally I suppose I have another diagram, we will see that this is what happens is, if I have a ceiling at the top, the fire causes hot gases to generate, fire causes, this is the flame, let us say flame. Now, hot gases will come out of it, hot gases, right, the air around, and the product of combustion, carbon dioxide, even various gases could be there, which we will see again. There, some of them are related to human health condition and all that. So, hot gases would be generated, and these hot gases will have a tendency to go up. Hot gases will have a tendency to go up, and they tend to accumulate over the ceiling. Hot gases will tend to go up, and they tend to accumulate over the ceiling, and this, when ceiling is all heated up, let us say the space in the space, this is the fire, and the space around is space around is something like this is the space. So hot gases let's say hot gases starts accumulating here, hot gases will start accumulating here. Now this gas, some of the heat will get transferred outside by conduction process through the roof ceiling, but it will also radiate back some heat to the furnitures and combustible material inside, and they will all get heated up. So initially started in one corner, but gradually it would try to heat up most of the combustible material in the room, and when almost all the materials, combustible materials in the room attain nearly ignition temperature, which can occur because now the heat is retained and heat is it's ready, it start heating the space, total space. More or less you will have some kind of an uniform temperature in the whole room, and a time will come when whole room will attain all the ignition temperature of the combustibles, which are average, on an average will be similar line. Suddenly you find there is an increase in the temperature. Suddenly you will find there is an increase in temperature. The point where this occurs, we call it flashover. We call it flashover. So there is a flashover, and this terminology is in some other places also, fire related or wherever. So there is a flashover point. Flashover means everything now has caught fire. This you might have experienced if you have burned some what do you call this, there is the rumble, what is that, agricultural waste, what do they call it these days, it's in news, huh? Not husk, not the husk, no, the thatch is prepared from what? See this, now they like, supposing you are burning, okay, supposing, let's say, forget about this, supposing you are burning something like straw in a heap, and you have started the fire in one corner, you will find that initially spreads a little bit, suddenly a large area gets captured by the fire itself. So that's basically kind of flashover is occurring. So once flashover occurs, the temperature rises rapidly, and then it continues there as long as fuel is available, combustible material is available, and then there is a decay period. So as the combustible material depletes, because they are already burnt out, then there is a decrease. So this is called fully developed fire, this flashover, then there is a decay period. But anyway, if I am suppressing it, then it might come somewhere there, if I am suppressing it, if I am able to suppress it, it might even follow this. So if I can suppress it, is fine. So this is called, this is the growth of fire in an enclosure, in a room, right. So fully grown fire and fuel depleted, this is flashover, we have already defined fuel depleted fire here, fully grown fire somewhere there. So actually it builds up, suddenly everything catches fire, then there is a steady period, maybe however small it may be, and then there is a decay, because fuel will now consume, it will get consumed and reduced, and that is how the fire occurs. So that is the process of fire in a building space, this is the kind of fire. Now therefore one thing, what is an indicator? Supposing I want to consider the quantify the fire, very dangerous fire or not so dangerous fire, or let me put it in appropriate words, very severe fire and not so severe fire. It would depend upon what? Temperature, and also the time. Supposing I have lot of fuel, then the steady period would be longer. I mean, say I am talking of fuel density, room volume remaining same, let us say. You have a higher fuel density, then it would require longer time to burn out, right. It will take longer time to burn out. So temperature and time, this is the two issue. So fires are defined by time temperature curve. Fires are defined by time temperature curve, right. Fires are defined by time temperature curve. We will come back to this again. So fires, you define fire. by time temperature curve. We will come back to this. Now, you see this small equation, not very complex. I said m dot. What is m dot? It is burning rate, rate of burning, that is rate of volatile generated per unit time, per unit area, multiplied by the fuel area, So, that is that this one will give me mass of volatile generated from the total fuel area in the room, multiplied by heat of combustion. This should be kilowatt, this kilowatt, right, delta Hc, heat of combustion. What is heat of combustion? It is the heat generated by burning unit mass of the material, completely burning unit mass of the material, or in mass means what mass I am talking of? I am talking of the volatile. When oxygen supply is abundant, there is no problem with the oxygen supply. So, delta Hc is heat of combustion, which actually is a amount of heat that will be generated by the volatile which is generated. So, this is the amount of heat that will be generated in the exothermic reaction, multiplied by a factor K, which is accounting for incomplete burning and things like that, some factor. So, quantity of heat that would be generated would be given by Q. Q actually it should be in QC. QC it should be written like this. QC, heat generated in combustion should be should be, it can be given by like this, right. Now, I was just telling you about effect of, so it is actually K m dot AF delta Hc kilowatt, QC quantity of heat, rate of heat generation in a way we are talking about, because this mass generated per unit area per unit time and multiplied by the area. So, the area part is gone. So, this is the quantity that would come out in per unit time, and each unit mass generates this kind of heat. So, total heat generated per unit time is this, that is why it in kilowatt or watts or whatever it is, and this is K is for incomplete burning. So, m dot is given by QF, that is the amount of heat generated per unit area, because when we talk of, we denote capital Q is a total quantity, right, for area is not involved, and this is small q you normally use for per unit area, heat flux, it is a heat flux per unit area. So, QF is a heat generated or heat generated by the fuel per unit area, right, which will come from here if I divide by AF. QL is a heat lost to the surrounding, because when we talked about earlier this diagram, if you remember, I talked about something like this, when we talked of fire, fire we said that some heat goes away lost, some heat goes to the fuel, again, and some heat is lost, and QF is the amount of heat generated by the fuel if there is a radiation back, if it is coming from the surrounding, right. For example, I said if there is a wall or ceiling, it will get heated up, gases they will heat up and they will supply the heat. So, if the heat it gets some more heat from there, that also should be added, minus whatever is the heat lost from the fuel, divided by latent heat of pyrolysis, latent heat for volatile generation, because we want to generate the unit mass of the volatile. How much heat do I need to generate unit mass of the volatile? How much heat I need? That much heat is LB. So, it is latent heat required to generate unit mass of the volatile. So, this is the total heat available divided by the heat required to generate unit mass. So, if I divide by this, I get the mass flow rate. So, that is what it is, right. So, I think this must have been also there in the previous diagram. You see QL is the lost, QF is coming to the fuel, and QE is coming from the environment, actually surrounding environment, surrounding environment. So, that is how I will be I define the mass flow rate. And if I have a ceiling, you can see that this component will be higher. If I have a ceiling rather than in open field, right, like 14th January you have Lori and you have Bhogali Bihu in Assam, right. So, they also burn a heap of straw, the house made small, so early in the morning, because it's a harvesting festival all over the country you find that. I think Pongal is also similar time. So, it's basically the crop that comes out, celebrate that all over this subcontinent in a way. So, somewhere you call it Sankranti, somewhere you will call it Lori. In western part of the country they call it Sankranti, Makar Sankranti they celebrate, Gujarat, Maharashtra. In the east they call it Bihu, and in fact south the other name. So, whatever it is. Now, you burn something of this kind there. This burning is open burning. So, when you have open burning, it finishes off much faster, and since this component is not there, the temperature rise is also lower. It complete fuel burning might take a little bit longer time, but the temperature rise here would be higher, because it is all enclosed. The gases occupy here and they tend to, so dissipation of the heat is less here. So, temperature, so burning rate is higher in case of, burning rate is also seen to be higher, gram per meter square per second is higher when I have an enclosure, Also, temperature goes high in such situation, right. So, because heat generated would be higher and it is retained in a way. So, effect of enclosure is like this. Now, other issue is the ventilation, because oxygen is the other thing. So, if you see this, here I had all oxygen was available all the time, no depletion, no constraint. Oxygen is no constraint or no, oxygen availability is oxygen availability in abundant, where this here you may not have sufficient depending upon the ventilation condition. So, if oxygen is not available, again it will slow down, because burning rate will be now governed by the rate of oxygen available. Volatile is available, all right, but the volatile cannot react, because the amount of oxygen required to react with the volatile generated, that will not be there. So, volatile will remain as it is, it will not react. Therefore, burning rate is controlled by the oxygen supply, where there is a constraint in oxygen supply. So, these are called ventilation controlled fire. Typical building is ventilation controlled fire, because it is not open. There is some windows, some doors, some of them may be open or may be closed, but some of them would be open, and if nothing is even open, you will have infiltration. What is infiltration? Leakages. Some oxygen will be there, but no oxygen. Supposing it is not there at all, then fire will simply extinguish itself on its own. It will consume all the oxygen present within the room, and beyond that it can't really sustain itself. So, we call that as ventilation controlled fire, where ventilation is in short supply, oxygen is in short supply, and when I have got fuel less, lot of oxygen, that we call as fuel controlled, because less fuel we call it fuel controlled, less oxygen we call it ventilation controlled, right. So, we will see that quickly, we will look into this. So, there are some, how do we model this, we will look into it. So, maybe this is how the fire behaves. So, we will break here. If you have any questions, I will take it and then proceed forward.